welcome back, and we're ready for the last part of the lab, and there was much rejoicing. Part 4, the Doppler effect. So first you got to know, what is the Doppler effect? Whenever you have a source of sound that is moving towards you, the frequency of that sound is going to be changed. If that source of sound is moving away from you, the frequency of that sound is going to be changed. Now, it's going to be your job to figure out, does it go up, does it go down, does it stay the same, and how does it depend on the speed? Now, there are formulas that will allow you to actually calculate the change in the frequency if you know the speed of the source. We're not going to do that. So we're just going to be looking at this from a conceptual standpoint. So what I need you to do is to go to Doppler Effect. So go ahead and click on this link, and I have gone ahead and done it for you. And so here it is. So the blue dot represents the source of the sound. So maybe this is a siren or something that's going to be emitting waves. And then over here, the green thing, that's going to be you. So you're the observer. This is the source of the sound. Okay, and then the first thing that you can change here is the source velocity. And it says in units of speed of sound. So if this is a -2, then what that means is that the source of the sound is moving away from you. So it's going to be moving to the left. And so that's why it's negative numbers. And so if it's a -2, that would mean that the speed at which this blue source of the sound is moving to the left would be 2 times the speed of sound. Okay, now you notice it's set for 0. So what do you think is going to happen? Well, it's not going to move at all. So this blue dot is not going to move at all because it doesn't have any velocity. Now, if we, on the other hand, if we put it over here, okay, now you notice it activates the thing there, and then we can pause it so that you can see what's going on. So let me go ahead and play it. But you see that the source of the sound is now moving to the right, okay, and then it's moving at a speed of 0.5 times the speed of sound. But we can increase that so it can be moving much faster. So if it's a 1, then it is moving at the speed of sound. So let me go ahead and put this back on 0. And then I'll go ahead and pause it. Okay, now, so our first observation that what you want to see is look at those red things. So the red things represent, let's pretend that it's a wave that looks like this. So that's the wave that is traveling outwards from that blue dot. Okay, where it has maximum amplitude, that's where there's a line. And then there's another line right here, maximum amplitude, and then there's a line right here, maximum amplitude. And then in between, those would then be the troughs. So you have crests are the red lines, and then troughs would be halfway in between each of those. So that's what those circles represent. So one of the questions that I'm going to ask you is, you should know what the distance is from here to here. So if it's a wave, it has a specific name. What do we call it? The distance, it's a length, it's a wave, put it together, and so then that's going to be what this distance represents. Okay, now look at the circles on this side over here, and then also look at your circles that are over here. Okay, do you notice, look at the distance from here to here, and then compare it to the distance on the other side in that picture there. Okay, you should notice something. So that if it is stationary, then it's sending out equal waves in all directions. Look at the frequency. So F is going to be the frequency that is being emitted by the blue dot. And you see it's 100 hertz. F sub 0 is the frequency being heard by you, the green thing there. That's the frequency that you're hearing. Look at those two numbers. You should notice something about that. So if we go back to the lab, then I want you to answer some of these questions. So before you run the simulation, predict what the frequency of the observer should be. Well, I just gave it away. But if the source of the sound is not moving, then you should be able to predict what's that person going to hear. Now you're going to click on the play button, which we already did, and were you correct? Okay, now we're going to set the source velocity to 0.3 times the speed of sound, positive 0.3. And then complete the following statements. So after you've run the simulation, answer this question. As the blue dot, the blue source of the sound, approaches the green observer, the wavelength got what? So look at the distance between the red things. And then, if that's what's happening to the wavelength, predict what's happening to the frequency. So, in order to do that, we're going to use this. The speed of the wave, which is going to be sound. So again, speed of sound is going to be equal to the wavelength times the frequency. Now this is going to be F for frequency there. Oops. Get rid of that. All right. So you can see what's happening to the wavelength by looking at what's happening to these red lines here. And so if this number is doing something, then you can predict what this thing is doing. So again, we're using the concept that 4 is equal to 1 times 4, but it's also 4 times 1. So if one of the numbers is getting bigger, the other number has to get smaller in order to compensate, and vice versa. Number 11, okay, now you're going to adjust the speed of the source so it's going away from the green observer. So as the blue source of sound moves away from the green observer, the wavelength gets what? So again, look at the red lines and see what they do. And then the frequency heard by the observer, does it increase or does it decrease? Now you are going to increase the velocity to 0.7. So you should have been using low velocities, but now we're going to increase the velocity to 0.7 and look at what happens to the red things, to the red lines, and then also look at what happens to the frequency. So what is the same about using a low speed and a high speed? And then what is different about using a low speed and a high speed? Okay, now I want you to go to the internet and find a video of a car or an airplane exhibiting the Doppler effect. So I want you to listen to what it sounds like. And then take a snip of the video and paste it right here. Now you might be wondering, what would happen if the speed is greater than the speed of sound. So we went from like 0.3 to 0.7, but now we want to go to 1. So 1 times the speed of sound is the speed of sound. So what happens to the red circles, and then this is going to be called a shock wave, and then fill in the following statement when a sound shock wave is heard by an observer. We call it a sonic something. And so you can probably find that on the internet. Alright, so that takes care of the Doppler effect. And so now you're going to do some of these post-lab questions, which I think are pretty self-explanatory. Alright, so that is our lab on mechanical waves. So our next scheduled lab is we're going to start talking about light. And we're going to be talking about reflection and then refraction. And then we're also going to do another lab on interference and diffraction. So until then, I'll see you.